So, fun with gas. We're going to do a couple of demonstrations, several demonstrations, and they all relate to the gases and their properties. But you guys are 7th graders, my understanding, and you had science classes in your school. Then I'm going to ask you questions. You don't raise your hand in college, right? In middle school, high school, you do to answer. But in college, you just say the answer if you know it, okay? So, question number 1. Give me an example of a gas that you know or familiar with. Don't raise hand, just give it to me, right? Okay, say that again. Hydrogen is one of them, right? Oxygen, wonderful. Helium, propane. Wow, you know a lot of sciences here. Okay, I want you to stare at this chart on the wall, and that chart is called periodic table of the elements. The elements that are known to scientists these days, they do include a good chunk of them gases. And you just mentioned some of them. Hydrogen. So that chart lists the gases with their symbols. Which one is the hydrogen? What symbol is the hydrogen? H. Can you see H, everybody? Yes. This is the first element here. That's H. And somebody mentioned helium, right? Did I see it? Okay, and which one is that? He. And somebody mentioned oxygen. Which one is that? O. We have O. We don't have O2, right? And what other gases you mentioned? Propane. Somebody mentioned propane, right? Is it here? No. Some gases are made up of those elements, but they are not listed. So these elements are the basic elements to make the universe, including propane. Does it make sense? Okay. Now, gases do exist in the form of molecules. That vocabulary is good to hear about. Molecules. And when you say O2, when I spoke about the oxygen, you said O2, that is a molecule of 2 atoms of oxygen that does not exist in the chart because that's the symbol, but it does exist in the air, O2. A representation of an O2 molecule is something like this. So you see the 2 atoms stick together. So this is a molecule, right, of oxygen. Hydrogen has a symbol H, but if the hydrogen is in the balloon, it won't be H's, just one H at a time, but will be molecules of hydrogen in the biatomic or diatomic molecule, H2. And this could represent a molecule of hydrogen. If we want to compare now the oxygen molecule to the hydrogen molecule, there's a lot to compare. What is the first thing you see different between those 2 molecules? Color is different, size is different, right? Let's focus on the size. Different. What similarities you see here? This is bigger, right? What similarities? Diatomic, we call it. 2 atoms, right? But this molecule here seems like multi-atomic molecule, bigger. And there's some molecules this big. Okay, you don't see them, right? But I mean, have a lot of atoms to them. So the number of atoms decide the size of the molecule. Let's again focus on the oxygen and the hydrogen. These are gases. And if you put them in a container, they will never sleep. Do you know what that means? They keep moving. If you are not sleeping, what do? You keep moving in the bed. Maybe you walk to the kitchen, you come back, right? So these molecules are walking all the time. I'm going to ask you another question. Based on the size, the mass applied, which molecule move faster? The small molecules, right? Did you know small kids run faster than big kids, right? So this one moves much faster than this molecule, 4 times as fast. Let's try to think of something realistic related to these molecules. Okay. If the 2 molecules are placed on the west coast of this country, California somewhere, right? And we're going to order them to run straight to New York, straight, okay? How much time this small molecule would take to get to New York running? 1 hour. 1 hour. Then, how much time this molecule would take to cross the same distance? Would it be 1 hour? No. More or less? More. About 4 hours. See? 4 times as much, or the distance or the time. So 1 hour, that's much faster than an airplane, isn't it? And even this one faster than an airplane. To tell you they move fast. You know what that means? If there is a gas in here that smells, right? Gives you some smell. And I open the bottle of that gas, everybody will be able to smell it quickly for the reason that the molecules move fast and they come to your nose and you smell them. Does it make sense? Wonderful. Now these are called physical properties. Physical properties. This is physics. This is not chemistry yet. It's not my area yet. But I want to dive into my area, chemistry. I want to look at the chemical properties of those molecules. For that reason, I brought 2 equal-sized bottles of the 2 gases that I'm interested in, the hydrogen and the oxygen. You cannot tell which is which because none of the gases has smell or color or anything. But because I labeled them when I filled them up, so this bottle here has the hydrogen gas, so it stands here. This bottle is the oxygen gas. What I'm going to do, I'm going to mix the 2 gases together. How do we mix gases? We know how to mix solids and liquids, right? But gases? Well, we try to take advantage of their movement to mix. So, one more thing before I mix them. The size tells the mass. So, hydrogen must be the lightest molecule ever in the periodic table. That's why it resides on the top. Very light compared to the oxygen. If I open this bottle that has hydrogen, the way it is standing right now, the hydrogen escapes quickly. I want to be able to control it. To keep it in, I'm going to open it upside down. Does that make sense? Yeah. Okay, so let's do that, and we just set it up here. So this way we guarantee the hydrogen stays in. Oxygen don't have to do that because oxygen is heavy enough to stay in the bottle. Make sense? Okay, so here it is. And I'm going to put the 2 bottles mouth to mouth like that. Now you understand the gas molecules are moving, then they are getting mixed, right? Make sense? I'm going to speed up the mixing process by doing this to it, right? So all of that is still physics. I'm just doing physical mixing. Make sense? So what I want to do, I want to check on the properties, chemical properties of those gases. I'm going to separate them like this. And I believe, you should believe as well, that we have a gas mixture in each bottle of the 2 gases we mix together, right? So what I want to check on is their flammability. Are they flammable? Do they burn, in other words? Yeah, okay, there you go. I thought that's not going to work. It's like 3 years old matches, but it works. So I want to ignite the bottle that has a mixture. And we'll see what happens. If the reaction goes on, if they are flammable, then you will notice fire, right? And if nothing happened, they are not flammable. Does it make sense? So we bring that little flame here to the bottle that has the mixture of 2 gases. You guys ready? Count 3, 2, 1, go. There you go. So what that tells you, that little explosion is an indication of a chemical reaction. That's an evidence of chemical reaction. So do you think the gases are flammable, combustible? Do they burn? Yes. Do both burn, or maybe one of them, the one has that properties and the other one is not? You cannot tell, right? We're going to learn more about it. But what I want to do is the same thing to this bottle. What do you expect to happen again? Now you know some science. Same thing, right? Ready. There you go. So, then the 2 gases together, they burn in a way that we can notice the chemical reaction. But we're talking about flammability. Hydrogen is known as, it is very flammable gas, explosive gas. However, you might not know the properties of oxygen. Oxygen is not combustible. It does not burn on its own. It doesn't, but it's important to burn anything. It supports combustion. Does that make sense? So that's what the job of the oxygen is. When you start a brush fire, if you start it in vacuum, no oxygen, it doesn't start. You have to have air come into it because the air brings oxygen and then it starts. And then if you bring more air, like wind, then you bring in the oxygen even faster, then the burning goes even faster. That's why it's hard to control wildfire when it's windy in California in the summer, if you remember anything. When it's windy, it's hard to control any wildfire. But when it's calm, maybe it's easier. because oxygen will come in faster and the burning goes on fast. Okay, so this is as far as those two gases. I want to write some chemistry here on the board for you. We said the oxygen is a diatomic, then we would write O2 for it to start the chemical equation. And we said also hydrogen is diatomic. What would I write for the hydrogen? H2. Now, we notice they reacted. What did they make? Anything reacts, any two things react, they must have produced something different. What is the product here? Thank you. No, it's H2O, right? Water. So that reaction produced a little water in this room in the form of moisture. Believe it or not, we increased the humidity in this room by a little bit from this reaction, because there were nowhere to go for those atoms of hydrogen and oxygen but to become water, and water is always in the atmosphere in the form of moisture. Does that make sense? All right, so this is called a chemical equation to represent the reaction. Now I'm to the dead body, but I never ever touched a dead body, even a bird, and I'm reluctant to do it. Anyone is willing to deal with that box for me? Okay, so let me, if I take you, what would you do? How are you going to handle it? Are you going to just take out the dead body for us? Okay, and then you take it out of the box? Okay, I'll let you do that when I run out because I don't want to see it. Is that okay? Yeah, I'll be scared. I won't have a good sleep if I see a dead body. You want to do that? Oops. How about I close my eyes and do it? That gives me an impression I did not see anything, right? Will that work? Am I here right? The right place? Yeah. Okay. Remember this what? Better bad. So there is a dead body here. Tell me what comes out. I don't see it. I don't want to see it until you tell me, okay? Oh, that's not dead body. See, look, curiosity. Everybody stands up to see. Wonderful. I'm glad it's not dead body for me. Well, it's dead something, right? What do you call this, my friends? Dry ice. Why they call it dry ice, not just ice? Can I call it ice? No. Why? Okay. So, is it cold? Real cold? Yeah. Do you know what? If I keep my hands on it for a little longer, it will burn him as if I keep my hand on a flame. You get burned by heat, by cold. Did you know that? So that's why I just touch it and move my hand quickly. So this is called dry ice because in reality it's dry against wet, right? You see, the surface is dry and it's everywhere, it's still dry. But if you put regular ice on it, it melts, it becomes wet. Does it make sense? Then this here does not melt. What does it do instead? It smokes. What is that called in science? Sublimation. Sublimation, right? So you see that smoke comes out. This is the sublimation. So what is the material here? What is it made up of? Is that really water in the solid form? No. Is that propane? No. What? Is that really oxygen? No. It is carbon dioxide. You guys familiar with carbon dioxide? Is carbon dioxide gas at room temperature or liquid? Gas. What is it? Do you deal with carbon dioxide in your life? Every 15 seconds you deal with it. How's that?
You breathe it out.
Yeah, you breathe it out. Every 15 seconds you breathe out carbon dioxide. And if we collect it and cool it down, it becomes solid like this. This is called dry ice. It's carbon dioxide in the solid form. And that sublimation, look what I'm going to do. I'm going to crack this huge bulk thing this way. And I know I'm going to create a mess here, but it's okay. You know why it's okay? Because the sublimation, it cleans itself up. I don't have to worry about it. Nothing wet left behind. And I take that big piece and put it here, and it makes noise. And this noise because of the sublimation, right? And you move it, still making the same noise. Oops. Sublimation. And I take this piece and put it in water. You see the sublimation. Yeah, what the heck is going on? These are properties of, that's so-called fun of gas, right? Fun with gas. Look at that. So, crack this one a little further. Oops, there you go. So what about this? This is a bottle. Let's stop that noise from keep going. And I'm going to put small pieces of this dry ice in this bottle here. And I'm thinking to stop that sublimation thing. So sublimation, as you see it, gas coming out. Gas need more space, but we have limited space for the gas here. Okay? And what do you think is going to happen? We'll see. Nothing happened. Where's the sublimation? You need more room for the gas to expand to. And here it's limited. Then let it go. Let's see what happens. And now we start thinking, oh boy, it's not really responding. Nothing is, oh, there you go. Now there is a response. Can you explain what you just observed? Why is that? Sublimation means the gas needs more room than the solid, right? Chemists are smart sometimes, right? So if I want to put this one real tight and even wire it, not to let it go for sublimation to stop it, do you know that would be a wise idea? That's called the stupid idea, right? You don't want to do that because it will explode, right? Okay, so it's going to pop again. We'll give it the time to pop. And we start talking about chemical properties. Gas expands, that's physical property. So the chemical property, we want to talk about it. Oh, there you go. Oops. Did I lose it? On the table, okay. Oh, here it is, thank you. These are a little foggy. So let's think of combustibility, the flammability. We know the hydrogen is flammable, maybe explosive even. Oxygen supports that. What about carbon dioxide? Can we burn it? No? Yes or no? Vote. Yes? No? Okay. So speculation is always a cheap experiment. What we do, we just put that flame in. What do you expect to happen? Either explosion or it goes out. And we do that again. Okay, we do the experiment twice. Same thing. What that tells you, it is not combustible. It does not support combustion either, does it? What about oxygen? This is a bottle of oxygen, new one. So this is not even burning, and I'm going to stick it in here to show you that oxygen supports combustion. Watch what happens. Catches fire. And you put it here, it goes out, and it has to be glowing. Put it in, catches fire. There you go. Out, on, off, on, off, on, off, like switch. On, off, as many times as you can do it. How's that? So it's telling you this gas here, the oxygen, support the combustion, while this stick is just glowing with enough oxygen, it's going to catch fire, right? So here is the big question for you guys. You are the scientists of the future, right? Okay, critical thinking question. We have oxygen in the atmosphere, don't we? What is the percentage? Anybody knows? Just say it. Under 20%. 20%. Around 20%. So 80% is what? What other gas in the atmosphere? What is it? Nope. Nitrogen. So I'm going to write those gases for you guys. So in the air, we have about 20% by volume oxygen. And we have about 80% by volume. Nitrogen is diatomic as well, N2. Wait, luckily it's not just oxygen, it's not 95%. Here's the question then. If you have to be, if the atmosphere is a pure oxygen, the atmosphere is a pure oxygen 100%, would you rather be a firefighter or mountain climber? Are you thinking? I like your answer. Firefighter or mountain climber? Why? You will have a losing job if you are a firefighter. You can't fight fire when it's pure oxygen. But mountain climber gets you away from the oxygen, as the oxygen always heavy stay in the bottom. Does that make sense? So, good percentages to know when you go back to your science teacher. You know these numbers, 20% oxygen when we breathe, right? It's not 100%. We don't want it to be 100%. Okay, so that being said, we're going to move on to a new thing. There's some other gases. You mentioned one of them, but I'm going to start from the beginning of the list for these gases. One of them is called methane. Methane, my friends, is the natural gas. You've heard of that term? Natural gas, underground, right? In science, we call it methane. So it has the formula of CH4. What element is C representing? Carbon and hydrogen, CH4, right? So, and a molecule of methane would look like this. Look how pretty this molecule is, right? So it's tetrahedral geometry, we call it, right? So this is a methane. Now, what do we use natural gas for? Have you seen those big buses running on natural gas? Some cars run natural gas, like those small Honda cars. So what is it for? Use it for cars, maybe. It's combustible, right? Okay, so the next gas from that is propane. I'm not going in order. So propane has 3 carbons. 3 carbons. And how many hydrogens comes to that? 8. So I have a molecule to represent, or representation to the molecule of propane gas, which is what you see here. Black is always the carbon. You see 3 carbons in this molecule? And the small spheres will be the hydrogen. Do you see 8 of them? And it looks like a small dog. It could look like two-way dog, right? This way and this way. So molecules, they have shapes, as this one has tetrahedral shape. So the propane has this shape, and I describe it as a puppy shape, right? This way or that way. So if this is the methane, combustible, what do we use the propane for? You use it all the time with your family, right? For the grilling, right? Barbecues, right? So combustible as well. And guess what? I'm going to keep moving for one more step, and I'm going to put in here the butane. Butane has 4 carbons to it. Come up with the number of hydrogens in a molecule of butane. 10. So to teach you how to get the number of hydrogens, if you know the number of carbons, math. Times 2 plus 2. Did you get it? Times 2 plus 2. So tell me, what will be the formula of the molecule that starts with 6 carbons and the rest hydrogens? 14. And that is called hexane. I'm going to show it to you. So on and so forth. Okay? So we have the butane. Now, another question for you guys, future scientists. If we go look at the sizes, as you go down, it's getting bigger, right? More atoms, bigger. How about the mass? Bigger, right? So if I tell you this is gas, and if I put it in the balloon rises. What about this one gas? If I put it in the balloon, will the balloon likely to rise or to sink? Will sink. So I have this tube here that has butane, compressed butane to it. You buy it from hardware stores like Ace or Walmart maybe. And I want to take this compressed gas into a bottle of those here, fill it up with the gas. As you guys should know, these gases don't have colors. None of the gas we deal with today has any color to it. So I'm going to fill this bottle with this gas and challenge my students, which is you, to see the gas. How do you see it? I mean to see when the bottle is full with the gas. Would you be able to tell if it is full, if there's no color? No. It's hard to tell, but in here we make it happen. So I just try it, you tell me if you see it full. And if not, then I come to you and explain how to see it. All right, so here's the gas, filling up. Look here. Do you see any gas flooding out of the bottle? You do? Okay. Wonderful, you do. So what about if I stand here? You guys can see that. You look here because the gas is thick, okay, you should be able to see it as flooding thick gas out of the bottom. Oh, yeah, see? You see that, right? Here is in the camera, even you can see that too. Right? How about you guys here? Be able to see that if you have not seen it? Yeah, so that's always the case. When the gas you're dealing with is thicker than the atmosphere, then you would be able to see the flow of it. That's refractive index. So now this bottle has butane. I need your help. To keep it in, should I cover it or just hold it like that? It's fine. Hydrogen, we put it upside down, right? Should I make this one upside down to keep it in? No. How about just like that with that cover? Is that fine? Yeah. That's true. So let's see if that is really true. What I would do, I'll test two things on this gas. Number one, physical property. It's heavy gas stays in the bottom of that bottle. Number two, it's a flammable gas because all those are petroleum products, petroleum used for burning, right? So then I'm going to use this glass tube here and pour it down the tube. If it is heavy, it's supposed to go down the tube, not rising from here. Make sense? And if I do it on my candle, it's supposed to catch fire when it gets to the candle. Does that make sense? You guys ready to see the miracle here? You're welcome to stand if you want to. But this is what I'm doing, just pouring the gas down the tube. Down the tube. Let's see if there is any left. We do it again. So what does that prove? Two things. The physical property, heavy, comes down, sinks, and catches fire. That's a chemical property, is flammable, right? So I want to do it again, but only if you guys are willing to help me look here and tell me, oh, that's enough. The bottle is full. Are you willing to do that? You guys have not seen it. I'm going to come to this group here. Look here. See how the bottle becomes full. There you go. It's all right. It's full. It's flooding. Doesn't take much, right? Okay. So we're going to do the same thing to it. So pictures are allowed or photos for this part of the experiment. If you think you can't catch it, it goes fast, but you're welcome to try. Okay, it's going to take a few seconds delay, but you can do it as video if you want to. And this is what I'm doing. Ooh. So I move this one fast. I have to, right? Let's see how much left. Oh, there was some left, right? So better move it out fast because it might catch fire. Okay, is that interesting to you? Okay, so heavy gases, they go down and then they catch fire. Okay, so we're gonna keep moving on that, and I'm gonna introduce something new. And this time, the new thing, something like this. Something like this. What is this? Everybody's familiar with this kind of product. What do you use that for? Same product. This is a sheet and this is liquid or something thick liquid, right? That kills germs. Okay, is it really safe to deal with? What I want to do, I'll take one of those sheets out and clean my hands with it. That's what we do, right? And then what do we do with it after we're done? We throw it away, right? So I'm going to throw it away here and show you how it burns. Did you think of it? So that burns quickly because the material soaked with is combustible. Did you think of that? So this is an alcohol. Alcohol is just another chemical that catches fire quickly. For that reason, want to be careful, not to be close to fires or any sparks, some sparks even, while you're dealing with that, or your hands are wet or anything, right? Make sense? And this is just educational because these days everybody using these sanitizers, right? What about this gel one here? Would it do the same thing? Yeah. It does. So what I will do, I'll bring a piece of paper and then maybe just soak it with this sanitizer, okay? And you're gonna see It's going to catch fire the same way. You might not think of it, but it does. See? Can you see it burning? There you go. I don't want to hold on it for too long, right? But it does. It does. Exactly the same thing. So this is something I meant to show you because it's circulating everywhere, and we need to know how to deal with that. Okay. So I'm going to go to other parts of the demonstration which still relate to the gases. And I want to ask a question about birthdays because I have balloons. I thought someone's birthday today, at least in this big group. For that reason, brought balloons. If not, it would be my birthday, but I go back to January 1st. Anyone's birthday today? Tomorrow? This week? This year. Wonderful. So this is for you. So I brought these two balloons, and I want you to think with me about what could possibly be in each one of those balloons, or in both. Are they the same or different? We're thinking of gases because it has to be gas. And I want to teach you something about gases. If you see periodic table like that, it's very easy to tell which elements are gases, which elements are not. If they are written in red, that stands for a gas. So this is a gas. Look, there are a few of them, right? So, and if the gas rises, should it be at the top or should it be at the bottom of the periodic table? Then would it likely be maybe hydrogen, maybe helium? I don't think it will be any one of those, right? So between helium and hydrogen, you guys use helium for your birthday balloons, right? This could be helium or could be hydrogen. How can we tell? We had a demonstration about hydrogen a minute ago. If the fire works on this balloon, it must be helium. Is that correct? No. What it should be? Hydrogen. So do you mind holding this for me? Just hold it like that, okay? Don't let it loose. Thank you. I'm not going to ignite it here. But I'll ignite this balloon, which could be hydrogen or helium, but I leave the judgment to you guys. You should tell me after you see my demonstration decisively if it is a hydrogen balloon or helium balloon. You guys ready? Again, pictures allowed because this is a spectacular thing to see. So I'm going to bring this little fire to the balloon, and you're watching the observation, and we ask a question. Ready? 3, 2, 1.5, 1, go. Ooh. What was that, do you think? Was it hydrogen or the helium? Hello, you did not tell me. Can I have that back? Thank you. So was it hydrogen? Yes, the explosion for hydrogen. Helium doesn't do that. So that's why your birthday party brings helium balloons, because helium does not burn like hydrogen. And what do you have? What else do you bring to your birthday party table? Candles and helium, good. But candles and hydrogen is the wrong combination. What do you think? Right? But for my birthday, because I'm a chemist, I bring hydrogen balloons like the one you just saw. Now, maybe this balloon has helium. Want to check? Yes. Anyone would like to come and try it like this? Yes. Wow, how many people are interested in that? Okay, so the one who comes here is the first one is going to tell me I'm going to become a chemist. Who's that? A chemist. Are you lying or telling me the truth? I'll do it. You watch me. Okay. 3, you count. 3, 2, 1.5, and 1. Ooh. What was it then? Hydrogen again, right. Okay, the very last thing, it's been going on for probably 40 minutes. Very last thing is something also new that I want to try with you. Listen. Now, this bottle here has oxygen, a small amount of oxygen compared to this bottle. Now, this small bottle has liquid, and this liquid has the hexane. Remember I told you I'm going to talk about that? That's the last thing. Hexane. Hexane is liquid. Methane, see, it's the same formula, but just more carbon or hydrogen. As the number of carbon and hydrogen gets bigger, larger, so the state of matter changes from being gas to liquid. And then if it is even bigger, you know, if this is like carbon 30 or 20 even, it becomes solid. That's how it works. Okay? So this is liquid because it has a lot of carbons, a lot of large molecules. Okay, so what I will do, I'm going to bring 2 drops of this hexane to this oxygen bottle and check the chemical properties of that. That's enough. Okay, now this hexane evaporates quickly. It does, really. So what I do, I just try to shake it to evaporate the hexane to become gas like the oxygen gas we have in here. And then I'm going to burn it. You remember, is the oxygen combustible? Yes. No, we said no. Oxygen support combustion, right? So is methane combustible? Propane, yes. Butane, you saw that, right? Same thing here, but I had oxygen added to speed up that burning. So what I will do, I will just bring a little fire to this bottle. We'll see what happens. You guys ready? Okay, do this, everybody. Ready? There you go. So that's even louder than ever, right? See how the oxygen make it even faster reaction? Okay, that concludes the demonstration for today. Hopefully you enjoyed it. Thank you. Thank you. Thank you. Now think of becoming a chemist. You will do more fun stuff like this when you are a chemist.